Hi, let's talk about differentials today. If you have a differentiable function, y equals to f of x, then the differential of y, which is denoted by dy, is defined to be f prime of x times the differential of x, which is denoted by dx. Okay, that's the definition of differentials. Now, this notation should not be completely strange because we used to denote the first derivative of the function f of x by f prime, and another notation we used is really just dy dx. Okay, and here if you take another look at this right hand side, that's exactly the quotient of the two differentials, dy and dx. One thing we want to compare the differential of y with would be the change in y, which is denoted in general by delta y. So the differential of y is in general defined to be dy equal to f prime x dx. But the change in y, which is the delta y, what that really means is if we provide a small change in x, let's denote that small change in x as delta x, okay? Then if we compare those two function values, one at the point x plus delta x, another is at the point x, then what would be the difference between those two y values? Therefore, the change in y is calculated by f of x plus delta x minus f of x. Let's take a look at an example to compare the delta x and to compare the delta y and dy. Okay, so here's a function we're given, y equals to x squared. It is differentiable, it is continuous, and we want to calculate at a specific point. Let's say for either case we want to calculate x is equal to 1. Okay, and dy or delta x are both set to be 0.01. Please note that these are really just small positive numbers for dx and delta x. With the definition of differential, we know that dy is calculated as f prime at x times dx. Now, if y equals to f of x is x squared, we know exactly what's the derivative of the function. It is going to be x squared, right, times, it is going to be 2x times dx. And we just plug in the values for x and dx to see that's 2 times 1 times dx, which is 0.01, and the answer for that is 0.02. Okay, so this is the dy we get for x is equal to 1 and dx is equal to 0.01. Now let's find the value of dy. Find the value of delta y. And delta y is calculated as f at x plus delta x minus f of x, where we have x is equal to 1. So the second term here should be the value of f of x at 1, and the first term here is f of 1 plus the delta x, which is 0.01. And we subtract these two numbers. There we have the function value at 1.01 minus f of 1. Remember, f of x is defined to be x squared. Therefore, I have 1.01 squared minus 1 squared. Okay, this value is really 1.01 squared. I'm going to use a calculator here. the square of 1.01 is 1.0201, and subtract that by 1 squared, which is also 1, we get 0.0201. Now let's compare the dy and delta y we got. For dy, we got 0.02, and for delta y, that's 0.0201. These two numbers are really very close. For that reason, in a lot of cases, when we have a differentiable function, the value of x is given, dx or delta x is a small amount of positive values, we can just take dy as an approximation of delta y, or vice versa. Okay? So, if you consider what we mean is, if you consider the function value f at the x value as x plus delta x, then by definition of delta y, recall that delta y is defined to be the value of change for y, that is f of x plus delta x minus f of x, right? So if you move this f of x minus f of x to the left-hand side, we see that f of x plus delta x is really just equal to the sum of f of x plus delta y. Okay? And remember we said if delta x is a small amount, this is going to be approximately equal to f of x plus dy, which is the differential of y. That is by definition defined to be f prime of x times dx. Okay? Therefore, as a formula we have f of x plus delta x is approximately calculated as f prime of x times dx by setting dx, the differential, is equal to delta x. This formula turns out to be a quite useful tool when we're trying to find approximate values. For a quick example, let's find an approximate value for square root of 16.5. Let's just try to find this by hand without using a calculator. Of course, you can verify our answer by the end with a calculator. Now, if we let the function, so here's the solution. Let's let the function f of x is equal to be something similar in this form for square root. So I would like to set f of x as square root of x. Now, by the formula we just talked about, f of x plus delta x is going to be approximately valued as f of x plus f prime of x times dx. Now, if we choose the value of x such that square root of x is easy to calculate, and also we don't want the delta x to be a very large amount, therefore we would like to have a value of x something close to 16.5. Okay, something that is really having a small difference compared to 16.5. And on the other hand, we want that choice of x value with an easy square root value that we can get. Of course, the natural choice for that value is 16, because square root of 16 is, okay, here's the reason, because square root of 16 is 4. We know that because 4 squared is exactly 16. Okay, so that's something we can conveniently get by hand. And also, 16 is close enough to 16.5. Therefore, the delta x here, that's the change, the value change in x, is calculated to be the difference between those two numbers. That is 0.5. Okay, and that's also what we want to take as the differential of x. Okay, we said dx is equal to 0.5. Okay, and that is because the delta x is here actually 0.5. Now if we have that by the formula, we know, by this formula up here, we know that f of 16 plus 0.5, we're plugging x as 16, dx or delta x as 0.5. That is calculated approximately as the value of f of x, which is f of 16 plus f prime. Now, if f of x is square root of x, then f prime of x is going to be half of 1 over square root of x. So this is half of 1 over square root of x. Okay, therefore we are going to have down here f prime of x, that's 1 over 2 times, remember x value we choose as is 16, and then times dx, which is 0.5. Okay, again, f of 16 here is really just square root of 16. We know that's 4, and we have that plus 1 over 2 times square root of 16 times 0.5. Everything here can be easily calculated just by hand. That's 4. That's 1 over 2 times 4. Oops, that's 4. And then times 0.5. Okay, so by the end, this is going to be approximately the value of 16. The value of square root of 16.5 is approximately 4.0625. Okay, so that is how we use the differentials to calculate an approximate value of a function at a position that is in general tricky to obtain by hand. Okay. Similarly, if I have the square root of, let's say, if I want to calculate square root of 25.1, you can use the same function, which is f of x as square root of x. The only change we need to make is now we're going to take probably x as 25, because again, square root of 25 is something easily calculated by hand. That's 5, right? And then the delta x or dx we're going to take is the change we had for x, which is 0.1. Okay? And all you need to do is to plug in these values for x and dx into the same formula here. Alright, so that is the example for approximation of numbers with differentials. Here's the homework for this section. Number 8, 10 are talking about definitions and comparison between differentials with dy's and delta y's, and number 44 will be similar to the last example we talked about. It's actually a cube root function that you will be handling, and you probably want to consider this hint here. The cube root of 27 is an easy number. That's an integer 3. Okay, that's the end of today's class.